Okay. Uh, yeah. So this will be uh, dedicated to IITG Advanced. Okay. So let's go for question number one. Find pH of the mixture obtained by mixing 50 milliliter of this much and okay. Right. So H3PO4 and Na3PO4. Oh, cool. So it's just like an acid buffer. So K1 is given, K2 is 10 power negative 8, K3 is that. Right. So not a big deal. It's a 0.2 molar, sorry, 50 into 0.2. So like 5 into 0.2 is 1 and 50 into 0.2 once again. So it's equal amounts. Cool. Then it's the same thing. Okay, and Na3PO4. You know what? Let's do it differently. So it's 50 milliliter of that and 50 milliliter of that. It's going to be 100 milliliter. So essentially it's a 0.1 molar. What's this? H? Seriously? Okay, 0.1 molar H3PO4. Right, so we can rewrite this question like this. So first of all, react it to give the middle two acids, and that will be 0.1 molar H2PO4 plus 0.1 molar H2PO4 minus. It should be HPO42 minus. Right, so like PO4 3 minus, and then we combine it to just get this thing. But okay, instead of writing it like that, you could go even further and write it like 0. So yeah, like each of these, can you actually write it further than that? I don't think so. There's no acid in between these. So yeah, like this is what it is in fact. Right, you can't reduce this question any further. Okay, so now this is more like an acid buffer where you have an acid and its conjugate base. Cool. And what is it? K2 is 10 power negative 8. K1 and K3 will be ignoring because yeah, like it cannot go to K1 backwards because KW upon K1, that's like 10 power negative 11, very big. The immediate next thing that you can do is do second ionization, right? You cannot go backwards, 10 power negative 11, very big. Third ionization is kind of also big. So second ionization. Right, so concentration of HPO42 minus will say it's almost the same thing as 0.1. 0.1 upon 0.1 times concentration of H plus, right? Because this dissociates into H plus and this thing, right? So it gives H plus and that. So concentration of H plus times all of that, that's equal to K2. K2 is 10 power negative 8. So there we go. Wait, what? 10 power negative 8 is kind of, no, that's small. That's very small. That shouldn't be happening. Okay, it's fine. Like for this to happen, you should have concentration of OH minus equal to 10 power negative 6, which is like, it's not a bad deal because it's basically like you had this initially and then you had some of it go back and in the process giving out OH minus. So for going back, the constant will be 10 power negative 6, and that's why this shows, right? That's the more understandable thing to do. And yes, 10 power negative 6 is still very small in comparison to 0.1. So yeah, that's how it's gonna be. What do you want to find? You want to find the pH of the mixture? Well, it's just 8. So it's C. Question number 1, C. Question number 2. Okay, when a drop of concentrated HCl solution is added to 1 liter of pure water at 25 degrees Celsius, the pH drops from about 7 to 4. When second drop of same HCl solution is added, the pH further drops to. So it drops 10 to 4. It's like 10 power negative 4. That's how much it's gonna be. So one drop contains 10 power negative 4 into whatever the volume is, that many moles of H plus HCl basically, and second drop will also contain the same kind of thing. So it's gonna be like 2 to 10 power negative 4. So it's like 4 minus 0.3, so 3.7. That's what it will drop to. So it's A. Right. H3PO4, its constant given, can form three types of buffers in three different ranges of pH. Most appropriate buffer was chosen to introduce buffer action at pH equal to 7.4. Okay, so pH equal to 7.4. Find the volume of 0.1 molar NaOH to be added to 50 milliliter of this guy to have buffer of pH equal to 7.4. Right. So, okay, this is fine. And if pH is like that, huh, for this to happen, what must happen is like the concentrations of acid and base both must be very big, and for that to happen they will be comparable, right? It cannot be that one of them is very very big and other is not that big. That will not be a good thing, right? And it's also like not possible in the first place. So cool. What that means is like both the concentrations are comparable. So your K value, Ka, that is approximately your that's approximately your concentration of H plus as well. So your pK is pH. So over here, look at that. pH is 7.4. Which of these is closest to 7.4? Of course, 8. 8 is closest to 7.4, and it's slightly less than that, so it's actually more acidic, right? And since it's more acidic, it's more aligned to H2PO4 minus, right? Okay, so there's a little more H2PO4 than HPO4 minus, right? And we can figure out how much that is by this thing. So, and what else do you want to find? You want to find the volume of 0.1 molar NaOH to be added to 50 milliliter of 0.1 molar H3PO4 to have a buffer of. Okay, cool. So first of all, let's find that ratio. So concentration of HPO4 2 minus upon H2PO4 minus, and concentration of H plus, which is 10 power negative 7.4. This thing is 10 power negative 8, so it's going to be 10 power 4, right? So 10 power negative 6, I think. So 10 power, sorry, negative 0.6. So 1 upon 10 power is 0.6. Like log base 10 of 2 is 0.3. So this is actually log base 10 of 4 is 0.6. So it's going to be 4 over here. Right, so it's 1/4. So HPO4 2 minus. First of all, we just need to convert everything to HPO4 2 minus, and from there we will see what we have to do. 0.1 molar NaOH, right? So V times 0.1. V is in milliliters. That's equal to, first of all, we need to get for the first ionization completely. So like 0.1 times 50 milliliter. So first you will add 50 milliliter, and that will completely convert to HPO4 2 minus, sorry, HPO4 minus only. And then you need to convert it to this thing a little bit. So this is going to be 1:4 ratio. So if initially you had 5, then 1/5 of that, right? 1/5 of whatever there was, that would be converted to this, right? So these many moles, the 1/5 of that thing, that's going to be 0.1 into 10. So add this, which is 0.1 into 60. So we should be 60 milliliter. But when you add 60 milliliter, first 50 milliliters just neutralize to H2PO4 minus, and then the remaining 10 milliliter takes 0.1 into 10 millimoles of this guy, converts it to that, right? And there's 0.1 into 50 moles of this guy, and that means now there is 0.1 into 40 moles of this guy, and that's exactly what we want. So 60 milliliter, and that's going to be D. Question number 4. Okay, a solution containing something concentration of X minus equal to 0.1 molar, Y2 minus is 0.01 molar. KSP is given on addition of, wait, KSP of what? MX. So M is added externally. If both MX and M2Y start precipitating simultaneously, find solubility of M2Y only in pure water. So we don't know what the KSP of M2Y is. We need to find that first of all. So if both are precipitating at the same time, then both of them have their QSP equal to KSP. So QSP of this guy mx, we don't know what concentration that was. So concentration times and x concentration was 0.1. This is equal to KSP of the first guy, which is 10 power negative 10. We don't know what KSP this guy had, but it had the same concentration of m, and well, it's m2y, right? m2y, so it's concentration squared, and then for y it was 0.01, so 10 power negative 2. Right, so let's just square this guy. So c squared of 10 power negative 2 equal to 10 power negative 20. And from this, it's clear that k is 10 power negative 20. Right. Find the solubility of this guy in pure water. Right, so if it dissociates by S, so S mole, like S into volume, those many moles are now gone from the solid, then the molarities of M and Y will be 2S and S. So that means 2S squared times S, that should be your KSP, which is 10 power negative 20. So S cube is 1/4 into 10 power negative 20. So S is, you know what, it's not good. Okay, write this thing as 10 power negative 21 into 10. So yeah, and then you will have S equal to cube root of 10 upon 4, which, so 10 upon 4 is like what, 2.5. So 2.5 cube root into 10 power negative 7. It's something bigger than 1. Oh, so you can write in exact figures, but what about that? That's nice. So 10 power negative 20 upon 4 to the power of 1 upon 3. That's exactly that. And no, yes, A is the way. I thought it's like JEE advanced, so it's going to be more calculation than in mains, but hey, they gave us a nice, like, less headache. Nice. For the following amino acid, so pK1, pK2, pK3 is given. So this one ammonium group, other group, there's only 2 of these, right? Okay. Why are there? Oh, okay, so this is like a charged species. Fine. pH of the isoelectric point of the species, pH at which net movement of species is 0. Movement of species. What does that mean? It's like reaction is not happening. I think that's what you mean. Right, so just what? That doesn't make sense. Okay. So pH at which there's no reaction or something like that. I don't know what you mean by that. Right? I don't know. Net movement of species is 0. Or is it somehow related to like its ionic mobility, that its ionic mobility is 0? So that would be when it's neutral and isoelectric. That probably does suggest that it's neutral. Right. I think that's the thing. There's no charge on it. That's what they want. So after pK1 and pK2, it will lose its charge, and then this species can behave like a weak, no, like an amphoteric species, and have like pK1 plus pK2 upon 2 as the thing, right? I don't have time to compare all the conditions and stuff, so just this plus that upon 2. Yeah, that will be what's going to, is this even correct? Because yeah, I think that is fine. So this plus that upon 2, 9 point something, right? So it's definitely not this, not that. It's gonna be this, I think, right? So it's B. Is this correct? Hope so, it's correct. So it's B, right? Okay. Next. objective, one or more than one. Which of the following form conjugate acid base pair in the right order? So acid then base. Well, yeah, this works. This doesn't work. No. This actually works. This also works. So A, C, and D. Yes. Question number 2. A weak acid HA has pH equal to 4. Which of the following conditions satisfy the same? pH equal to 4, weak acid. Yeah, so 10 power negative 3, that is your C alpha value. Okay, so C equal to 10 power, sorry, 10 power negative 4 is the C alpha value. Alpha 10% is 1 upon 10, and yes, this works. C is this thing, K is that. Okay. So alpha squared upon 1 minus alpha is 10 power negative 4. So alpha would be 10 power negative 2, and this would be 10 power negative 4. Yes. Okay, B also works. C, concentration of A minus equal to that. Yes, it works. Ka is 10 power negative 2. Alpha is 10%. Wait, what? Ka is 10 power negative 2. Alpha is 10%. Oh god. Okay, alpha is 10%, like 0.01 times concentration. That is pH is like, okay, so 10 power negative 2 times 10 power. Okay, so concentration will be 1. Then no, this doesn't work. So B, A, and C works. A, B, C. Question number 3. Which of the following will function as a buffer? NaCl plus NaOH. I mean, it's salt and it's a base, so it's a basic buffer. But wait, both of these are like strong electrolytes. So if you add acid, it will just react with it. It won't. Yeah, so it's not a buffer. Fine. This guy. So it's H2PO4 minus and HPO4 2 minus. Yeah, there's like, this might actually work as a buffer. When you add acid to this thing, some of it will get eaten up by HPO4 and it will convert to that. So C works. B, SO4. No, like H2SO4 and HSO4 ones. I mean, okay, it is acid and base, and it's conjugate base, but you know, it will just go to SO4 2 minus, right? Yeah, and any acid that you provide it will not do anything with it, right? It's a strong acid, so why would it do anything? Or is it that you have to consider HSO4 as a weak acid, but then still H2SO4 is a strong acid, so maybe not. NH4Cl plus NH4OH, so NH3 and NH4 plus basically. Yes, this can work because NH4 plus is like a weak acid. It will give, and this guy is its conjugate base, so of course. So D works. C works. We don't know if D works or not, but it does look like it will work, except that H2SO4 is a strong acid. D and C are definitely going to work, so yeah. Question number 4. Which among the following statements is or are correct? pH of 10 power negative 8 molar HCl is equal to 8. Well, yes, that's correct. Conjugate base of H2PO4 minus is H. Yeah, that's also correct. pH of 0.1 molar NaCl aqueous solution is half of pKw. Yes, it is. Why did you write it like that? So yes, it's 10 power 7. Okay, I mean 10 power negative 7, so yes, it's gonna be 7 over there. Wait a second, no, A is just wrong. Sorry, A cannot happen, right? This doesn't make sense because 10 power negative 8 molar HCl. Oh, yeah, that doesn't work because then the concentration of OH minus, that would be 10 power negative 6, which is more than your H plus concentration, which doesn't make sense, right? Yeah. So A is definitely not correct. A is not correct. B is correct. Yeah. C is also correct. Ionization of water increases with decrease in temperature. No. So B and C only. Okay. In which of the following pairs of solutions is there no effect on the pH upon dilution? Solutions, is there no effect on the pH upon dilution? Right. So a buffer could be like that if its concentration don't decrease a lot. That is, uh, something like an amphoteric species or a weak acid, weak base salt, that would work. First option is NH3 and NH4 plus. So remove this SO4 minus, it's essentially just NH4 plus. And yeah, these are like comparable in quantity, so it's a buffer basically. C is HCl and NaOH. Oh, no, this will have difference. And yeah, these are like big concentrations, so it will have an effect. Which, so B will work, of course. A will work. D will, it's like 0.1 molar KCl and 0.1 molar HCl. No, KCl is just inert and HCl, its pH will change. So yeah, like A, B, and no, not C. So just A and B. Which are fifth, A and B. Which of the following solution in water acts as a buffer? 0.1 molar of mole of NaOH plus 0.15 mole of CH3COH. Yes, it does, because 0.1 mole of NaOH will just neutralize 0.1 mole of CH3COH, and then the other 0.05 mole that will be still there, so it's a buffer now. CH3CONH4, it's, I mean, when you add H plus to it, it will change, right? It will get some of that CH3COH over there, and this won't actually, like, it's not meant to be a buffer, but does it work like a buffer? No, it doesn't. It doesn't. There's just this like a lot of CH3CO minus. That's all it is. When you change, when you try to add H plus into it, it doesn't resist getting that H plus, right? It just takes it. The main thing of why it doesn't change its pH in like during dilution, right? That's because the H plus generated and consumed are the same when there's nothing else added in there. When there is something else added, everything starts to become difficult, right? So no, this will in fact, like, it will not act as a buffer. 0.5 mole of pyridine plus 0.5 mole of pyridinium chloride. Well, I mean, yeah, it can kind of act as a buffer. It's just acid and conjugate base, maybe. Okay, so AC and then 0.25 mole of NH4Cl plus 0. No, NaOH. It's just in more quantity than what we need. Like, it will just neutralize this completely, and after that also there will be 0.25 mole of NaOH remaining. So no, D is not gonna work. A works, C works. That's it. Pure AgCl was added to 0.01 molar AgNO3 solution, 0.025 molar KCl solution, and both suspensions are shaken well. Okay, what is the approximate ratio of ECl minus in the first solution to the Eg plus in the second solution? Okay, KSP, anything, nothing is given. Okay, approximate ratio of ECl minus in the first solution to the Eg plus in the second solution. 0.01 molar Ag plus over here and 0.025 molar Cl minus over here, and you want an approximate ratio. Well, you could probably have Cl minus in the first solution to the, so call this guy, I mean this concentration, call it as C1. So C1 times 10 power negative 2, that thing is the same thing as C2 times 10 power, well it's not 10 power, it's like it is 2.5 into 10 power negative 2. So C1 upon C2 is 2.5. That is assuming that these concentrations don't change a lot, right? So approximately 2.5 maybe. Okay, it's not 8, right? Unless given what your KSP actually is, we can't actually say anything for sure, but maybe it's like that. Okay, next, question number 8. Buffer solution can be prepared by mixing equal volumes of 0.1 molar sodium acetate and 1.5 molar acetic acid. Sodium acetate. Yeah, acetic acid, of course. It works. 0.1 molar sodium acetate and 0.5 molar hydrochloric acid. Sodium acetate will take 0.5 molar hydrochloric acid, convert to sodium, convert to acetic acid, right? So it will be a buffer in the end. Yes. 1 molar ammonia and 1 molar ammonia chloride. Yeah, it works. 1 molar ammonia is 1.5 molar sodium hydroxide. But no, that's basic. That's basic. So it will be a basic thing. Okay, yes, but will it be a buffer? NH3 as an acid? I've not seen it like that. Sodium hydroxide in water. I mean, you could think of it as an acid, but then if it was an acid, then 1.5 molar sodium hydroxide, won't it just like overpower it or something, right? Because there is just a lot of OH minus right there, so it will overpower it, right? Of course. So no, I don't think D works. Yeah, so C works, B works, A also work. Yes, so ABC. Question number 9. Which of the following statements are correct about the ionic product of water? Equilibrium constant of water is bigger than ionic product of water. I mean, okay, that's kind of okay, fine. So the equilibrium constant, that will be concentration of H plus concentration of OH minus upon concentration of H2O squared, and then it depends in what terms you want the concentration. But yeah, concentration of H2O, that is something like 1 upon 18 into 10 power 3, as we saw so many times, and that's less than 1 for sure. So this guy square is also less than 1. That means it's bigger than this thing, right? This is bigger than that. So yeah, equilibrium constant is bigger than ionic product. So A works, I think. PK is bigger than PQAW. No, if this equality is happening, then the opposite inequality will happen for this guy, because negative log base 10, not positive log base 10. Kw of water becomes approximately equal to 10 power negative 12 at 300 Kelvin. No, 10 power negative 14 at 300 Kelvin. Ionic product of water at 25 degrees Celsius is 10 power negative 14. Yeah, that's correct. So D is also correct. Was B? No, B was wrong. So AD. Question number 10. Question number 10 is, a buffer solution can be prepared from a mixture of sodium acetate and acetic acid in water. Same kind of question. Yes, sodium acetate and hydrochloric acid in water. Yes, as we just saw. Ammonia and ammonium chloride. Yes. D, no. So ABC. Right, ammonia and ammonium hydroxide, no, I don't think so. Sorry, sodium hydroxide, no. So yeah, that's nice. Question number, so it's comprehension type, fine. Okay, so comprehension type, question number 1. How many okay, so comprehension 1, and for that question number 1. Alright, so what's the comprehension? Pure water is a weak electrolyte and neutral in nature. H plus is exactly equal to H minus CS. When this condition is disturbed by decreasing the concentration, yeah, we know that. This is exactly the change. So they just like, okay, so they just gave three formulae and okay, cool, fine. Just gave all the formulae and solve this. That's what they are saying. Uh, that that's actually fine. Oh, so also this data, that's the most important thing. pKa is 4.7447. I think that's log base 10 of 3. No, that's 10 times more than that. 10 power negative 4.7, all that stuff. Whatever. And pKb is this guy. Okay. pKw is 14. Okay, cool. So pKb and pKa for what? For some acid, for some base, like that. Okay, when 50 milliliter of 0.1 molar NH4OH is added to 50 milliliter of 0.05 molar HCl, the pH is, so basically it's 0.05 molar NH3 and 0.05 molar NH. Oh wait, no, it's gonna be 0.05 upon 2 molar NH3 and 0.05 upon 2 molar NH4 plus. Right. So pH is the same thing as pKa in this case. Yes, I think so. What's the pKa? It's 4.7447. Oh, that's very nice because what that means is like it's an acidic thing. So yeah, C. So first C. What are these other numbers? I don't know. I don't know what these numbers are. Yeah, this should work, I think. What could not work over here? I don't get it. Okay, 0.01, that's 10 power negative 3 NH4Cl aqueous solution has pH. Just NH4Cl, so it's like NH4 plus 10 power negative 3 concentration. What is Ka? It's 10 power negative 4.7447. Okay, that's your Ka value. And what's your concentration? Concentration is 10 power negative 3. Okay, and what do you want? You want the pH. Oh, come on. So can we do the same thing? Let's say that it's like dissociation is very negligible and stuff, and yeah, then that just means like C times of alpha squared, that's K. You can write this thing as C alpha squared equal to C times K, and then square root of that. So your pH will just be negative log base 10 of this guy, which is negative 1 upon 2 log base 10 of that. So like log base 10 of C, or just write it as log C plus log K, right? That must have been over here as well. So this is okay, that's for salts and stuff, whatever. But the thing is, yeah, this is how it should be, right? For C alpha form. Yeah, what else could it be, right? Okay, so what was I doing? Question number 2. Yeah, so log of C, that's just 10 power negative, so it's gonna be negative 1 upon 2 into negative 3, and log K, that we already know, so like this negative all that stuff. So actually you can write it as this directly. 4.7447. That's assuming it works with that approximation, right? We'll see what we get. That's your pH, isn't it? So this is 7.7447 upon 2, which is, let's see, 3.5 carried on, and then 8, 5 carried on, to 7, and then yeah, like 0.5, and then it's 8, 5, and yeah, for and 2, 3.872. That is your pH, which is approximately 4. So 10 power negative 4, that's the concentration of H plus, and that means your degree of dissociation, that was 10 power negative 1, right? So basically 10 power negative 3 times 10 power negative 2, that was 10 power negative 5, which is, yes, that was close enough to pk. And 10 power negative 4, that's also big, much bigger than 10 power negative 7. So it works, everything works out. Cool. So yeah, like this has pH this much, 3.8, all of that. It isn't there. It isn't there. Why? This should be there. What? Why is it not there? I don't understand this. Well, it's definitely not 7.126. No, it's not. Oh God. So C alpha, I think squared is C times K. So yeah, that should work out. Like, I don't understand this. Why doesn't it work out? What is going on? Now it's just not there for some reason. Like, how? Okay, I don't know. So question number 2 is, it's weird. We did do it correctly, right? We took pKa is like that, it was correct and everything. Why did it work out? NH4Cl, it's just NH4 plus basically. I don't know, man. Or you could think of it as NH3 plus HCl, but then once again, it's the same thing. HCl is like a very strong acid, so you could probably use this thing over here. Salt of what? Weak base and strong acid. Okay, so it's gonna be this guy. So half of pKw minus pKb. Oh, okay, now I understand. So like this pK value was not for NH4 plus. Instead, you had to use NH3. For that, you need to use pKb, and that's seriously, they just want us to use the formula and not rely on anything. Okay then it's fine. We're just gonna use the formula and get it done. That's what they want us to do. Okay, so second formula, so half of pKw, which is 14 minus pKb. pKb is this guy 4.7447. Okay, minus log C. So concentration is 10 power negative 3, so it's gonna be plus 3. There we go. So half of 17 minus all of this stuff is 4.7447. So it's gonna be 3 and then 5 and 5 and 2 and point and 1 that upon 2. So 6.1 to 5 carried on, 7 5 carried on. So it's like 6 and then 5. There we go. Yeah, 6.12765 basically, which is approximately 6.128. But yeah, 6.127 also does. So A is the correct answer, I think. Third is 50 milliliter of NaOH is added to 50 milliliter of 0.1 molar CH3COH solution. The pH will be. So now it's gonna be 100 milliliter of 0.5 molar, because the moles will be the same. So 0.5 molar CH3COONA. Right, so it's like what? It's a strong base and a weak acid basically. And its molarity is 0.5. So just use this guy. Where is it? Weak acid, strong base, right? It's half of 14 plus pKa, which is 4.7447 plus log of C, and C is now 0.05. Log of that, okay, log of 5 into, okay, 0.05, 5 to 10 power negative 2, which is actually like what, 10 power negative 1 upon 2, right? So plus log of that will be minus 1 minus 0.3. Yeah So that's actually minus 1 point. It's like half of 14 plus 3 point, what's this? 3.4447. Yeah, so half of, if I just want to approximate, this will be 3.5, so basically 17.5. And no, let's not approximate that. We can do it directly, right? So 17.4447, and then half of that will be 8, and then will 10, so 0.7 and 2235. Is that in the options? Yeah, 8.72 something. So C. And then fourth, okay, 1 mole CH3COH and 1 mole CH3CON are dissolved in water to form 1 liter aqueous solution. The pH of the resulting solution will be, so it's the same thing as, so 1 mole and 1 mole, that's very nice. So it's the same thing as pKa, right? And that is this guy, 4.7447. So B. 50 milliliter of 0.1 molar NaOH is added to 50 milliliter of 0.05 molar CH3COH. Okay. Wait, what? That doesn't make sense. 0.1 molar NaOH and 0.05 molar CH3. Let's just gonna overpower it basically. The pH of the solution. I mean, okay, that doesn't make sense at all. It's just gonna overpower it completely, and it will be like 100 milliliter of 0.025 molar OH minus basically. Right, so 0.025, right, negative log base 10 of that guy, that's our POH. And what is this value? It's like 25 into 10 power negative 3, which is 1 by 4 into 10 power negative 1. So this thing will be negative of negative 1, negative 2 into 0.3, which is 1 plus 2 into 0.3, right, which is 1.6. 1.6 is our POH. Why is that so small, right? Like, that should not be happening. Yeah. Okay, so 0.25 times 10 power negative 1. That's what this thing is. Well, that's correct and all, but it's still very small. Okay, so 1.6 is POH. Our pH will be 7 minus that. Oh, it's small in numbers, but actually it means a very significant thing. Like, it's very basic, basically. So, sorry, not 7 minus that, 14 minus that. 14 minus 1.6. So 4 and point, and then we got 3 over that, minus 1 is 2. So 12.04. Is that in there? It's question number 5. Well, okay, it's 12.39 is in there, and maybe that's the thing. So B. It's like highly basic, of course. And then there's some stuff because of this guy over there, but we kind of ignore it. Right. So fifth is done. Let's go to the next one, which is compression number 2. So second. 20 milliliter of weak base BOH is titrated with a strong acid HA. Following experimental data of pH is observed after addition of given amount of acid HA at 219 Kelvin. Okay, so 20 milliliter of weak base BOH, strong acid HA. So first it's 9, that's it's basic. So when only 10 milliliter is added, so pH of only weak base must have been even bigger, of course. 10 milliliter is added, that means, yeah, so like 10 milliliter of BOH is still there, and 10 milliliter of just B minus is there now. So that's when, so this thing is like actually equal to your pKb in that case, right? Of course, that's how it should be, because these are equal. This thing is your no, not the pH, we want the POH. So the POH, that will be 14 minus 9, which is 5. So 5 is your pKb, right? So that's nice. So now we know that pKb is 5, or just directly Kb is 10 power negative 5, whatever. Yeah, cool. And then what? Then you add 16 milliliter. It's still not gone, so it's like 4 milliliter of BOH and that, right? So maybe we can find the concentration by this thing. No, we can't actually, because look, it has some moles, 16 milliliter over there, so 4 milliliter of that concentration of POH, that many moles are remaining, and others are converted to this. So now your pH is different. It's 8.4. Are there concentration effects over there? I don't think so. Okay, and then you have 30 milliliter. That's quite a lot. So it's just gonna overpower this. And okay, I understand. I understand. It's gonna overpower this thing. Uh, and then pH is now 1.7. So wait, 30 milliliter of that. So that 20 was used for POH, and the other 10 milliliter is now in a 50 milliliter thing. So it's oh, so you still don't know the concentration. Oh no, oh no. We assume that the concentration of BOH and HA is equal, but without that, this is actually wrong. Right, that doesn't make sense. Any other information that's given? No, nothing's given, right? Okay, so right now it's basic, then it becomes slightly more acidic, and then becomes very much more acidic. Okay, how am I supposed to do this thing then? Credibility of peak base, BOH. Look, it's still basic, so it's still going on. When you add 16 milliliter, it became 8.4, slightly more acidic, yes. And just from this data itself, can you actually figure out anything? I don't know. I don't know. Don't know the concentrations, don't know anything. Like, it just makes it automatic. But at least we know that it's gonna be a buffer solution thing, right? Because if the concentrations are comparable, then of course it's gonna be like a buffer solution. Yeah. And at least right there, it was like changing very slowly, so it's only changed by 0.6. That means, yeah, it was kind of like behaving like a buffer solution, and then it just changed rapidly, right? So let's talk about these two, the concentrations in these two. This has pH 9, and this is, it's different. Okay, so what you know, the concentration of BOH is going to be P plus times concentration of, okay, upon concentration of BOH. OH minus. That thing is your Kb value. So applying P on both sides, pKb is POH plus P of this guy, so basically like log base 10, so negative log base 10 of concentration of P plus upon concentration of POH, right? And hey, we can use this equation because, right, so like pKb1 minus pKb2 is the same thing, because Kb is, it doesn't change. So applying delta on both sides, that's the change basically. Yeah, so your delta POH, that thing is log base 10, like the change in this guy, right? So concentration of P plus 2 upon concentration of P plus 1 times, okay, upon concentration of POH. To, you know what, no, let's go for some other thing. So degree of dissociation of that, like how much of it is converted to that, we need like some kind of fraction for this. Yes. we'll call that X. So the initial guy's concentration, just call it concentration as C, and this will be X, C minus X, right? So it doesn't, like, dilution effects can be ignored because it's a buffer. Then that means, yeah, even if your, like, X is the would be concentration if all of those moles were in the 20 milliliter. So yeah, and similarly that thing. So you can write this as, I don't know, x2 upon x1 upon c minus x2 upon c minus x1. Cool, right? That's nice. Okay, so your delta POH over here, so it went from 9 to 8.4, so it's a negative 0.6 over there. And yeah, like, you know what, your X value is somehow dependent on like, it's proportional to how much of volume of this HA you add, right? You know what, instead of saying this thing, you just use moles, so N. Cool. Then your X is basically just the molarity times the volume that you have, right? So you can use that. So this thing will just be V2 upon V1, and this thing will be M times V2 minus M times V1. Cool. And basically, what is V2 and V1? It's 16 and 10. So this is going to be 16 upon 10 upon N minus 16 M upon N minus 10 M. We need more space for this. Just move this in the front. So negative 0.6 is log base 10 of 16 upon 10 divided by N minus 16M upon N minus 10M. Cool. Now we can do this. Yeah. So we can find the total moles that were initially present, and also the molarity by this equation, hopefully. At least a relation between them. So this will be like N minus 16 upon M, N minus 16M upon N minus 10M upon 16 upon 10, just taking the reciprocal of that. That will be, so it's gonna put negative sign on the front, and then that we cancel with that, and then the so 10 power 0.6, that's 4 basically, that goes over here. So 16 upon 10, that's gonna be 3.2. Yeah. So N minus 16 M is 3.2 N minus 32 M. So 16 M is 2.2 N. Well, there we go. So now you know what N is. N is just 16 upon 2.2 M. Okay, that's like much better than knowing nothing, at least. Yeah, and now what do we do with that? Hey, we know what the POHs were. Wait, that's the pH. Oh no, this should have been plus over here. Okay, this was wrong. Oh no. So this should have been 10 upon 16 upon 10 to 1 upon 4. That would be 0.4 in that case. And then all of this is wrong. This is so lengthy. Why is this so lengthy? So like 4 upon 10 is actually better. So 4 N minus 160 M is 10 N minus 160 M is 4 N minus 40 M. So 6 N is 120 M. Now we get it, finally. N is 20 M. Right, so let's plug that in one of these equations. So first you have pH equal to POH equal to 5, which is pKb plus log base 10 of all of that. So pKb we don't know, plus log base 10 of, well, X is basically just volume times molarity of the acid, right? So that's M times initially the For the first guy, volume was 10, so m into 10. So it's 10m upon, so c minus x, so 20m, or I should say n minus x. So x was, once again, just 10m. Look, that's 1. Hey, you know what? Our thinking process was correct. Yes, this was in fact the buffer, like that had equal amounts. So yes, these actually have the same molarity. Wow, well that's nice. Same molarity, and you also know that n is 20m. So the number of moles in this guy is 20 times the molarity of the acid, but the molarity of the acid is the same thing as the molarity of the weak base. Hey, yeah, I mean n upon 20 is m. Okay, that's obvious, I think. Okay, that makes sense. And I should say like millimolarity or something, because you are actually dividing by milliliters and not liters, but it works out anyway. Yeah, right. So it's like 10 power negative 3 and stuff, but yes. Okay. So molar, instead of saying m is like molarity, I should say it's kilomolarity. So 2 kilomole, 3 kilomole, or something like that. Then it would be correct. Okay, so this thing is just 1, then this is gone. So pKb is 5. Hey, that is super nice. So we know pKb is 5. Cool. And what else do you want? pKb is 5, and what else? Like, you want to figure out the concentration of acid HA. Right. Once you know what pKb is, you can go for the second condition and get some other stuff done. So once again, POH, right? What was the formula once again? POH is pKb plus log base 10 of all of that. POH was 0.6 more than that, so 5.6. So 5.6 minus pKb, that's a 0.6 basically. So yeah, that is log base 10 of, now it's 16m upon 20m minus 16m. Man, these fractions are nice because it doesn't matter what these actual values are. So 16 upon 4, that's going to be 4 over there. Well, okay, that's obvious, and it's from where we got everything, so this should be obvious. Yeah, so we can use the third condition now. It says that when you have 30 milliliter of this added, and now we know that the molarities are the same, right? So it says that when you have 30 milliliters of it added, so basically it's just like 10 milliliter of HA working, but its molarity is 1/5 of what it should be. Then the pH is this guy. So what is like the concentration of H plus it's 10.81.7. So 5 times of that thing is the actual molarity of the base and the acid, both, right? Yeah, and this is like, so 10 power negative 2 times 0, 10 power 0.3, which is 10 into 10 power negative 2. So 0.1 is the molarity. Cool, we got it. Right, 0.1 is the molarity, we got it. Now we can find everything. And Kb was 10 power 5, and 0.1 is molarity. pKb, so no, Kb. Wait, pKb was 5, Kb was 10 power negative 5, that is right. Finally. Okay, let's start. Concentration of acid HA is 0.1, so fix A. Oh, so you can write it as 6th directly. Okay, A. Then 7th. pH of the solution at equivalence point. Equivalence point, that's when it's completely neutralized, I think. Yeah. And that is, we assume it will be completely neutralized. Right. So now we know what, sorry, K, yeah, it's Kb actually. So now you know what KB is. We can figure out the reverse KA, which is 10 power so 14 10 power 9. Okay, and at equivalence point, uh, what will be the pH? What's the concentration though? I mean, both of them have 0.1, so for that you will need to add 20 milliliter of HA. So now it's half of its initial concentration, right? So it's gonna be 0.05. That's the concentration. It's 10 power negative 9, I see. So this is 0.1 upon 2, and that means alpha square upon this alpha is 2 into 10 power negative 8. So alpha is approximately square root 2 into 10 power negative 4. Yeah, works. Definitely works. C alpha is, in that case, what? 1 upon square root 2 into 10 power negative 5, which is still bigger than 10 power negative 7. So yeah, it works. 1 upon 2, that is 0.7 something. So yeah, no big deal. It works. Right? Okay. What they want? They want the pH of the solution at equivalence point, right? So yeah, that's our thing. That's your concentration of H plus. So your pH, that will be 5 plus log base half of log base 10 of 2, which is 0.3. So that is 5.15. Yeah, D is the thing. Cool. And let's also go for 8. Oh no, why did I erase all of this? Yeah, I know what was the thing. So yeah, 8th. pH of the solution before titration would be cool. So 20 milliliter of 0.1 molar BOH with Kb equal to 10 power negative 5, right? Yeah, we know everything now. So 0.1 alpha squared upon minus alpha is 10 power negative 5. This thing is going to be 10 power negative 4. Alpha is approximately 10 power negative 2. Yes, it works. It's small compared to that. So we want the pH. C was 0.1, so 0.1 times 10 power negative 2, that's 10 power negative 3 is concentration of OH minus, right? OH minus, not H plus. So POH is 3 and pH will be 40 minus 3, which is 11. So it's C, 11. Right, cool. Next, 9. The equilibrium constant for the reaction of BOH with HA at 298 Kelvin. What is the reaction like though? It's BOH plus HA gives, that is very weird. Equilibrium constant for that. Okay, this gives BA plus H2O. So you mean concentration of BA? What? No, that's just infinity in that case, because yeah, that is not how it should be. What kind of equilibrium constant do you want? Because if it's a strong acid, it will just completely convert to that. So it's like it's almost reversible, you know. So sorry, almost irreversible. There's no equilibrium over there, right? So no equilibrium constant, or if it was there, it would be very, very big, and doesn't make sense, you know. Doesn't make sense at all. 10 power negative 8, 10 power 8, 10 power 9, 10 power 10. I don't know, man. What does this even mean? Like, concentration of PA upon times concentration of H2O, concentration of HA. There is no HA. Come on, this is not there. This cannot happen. Right? So no, this is not there. 9th is weird. Just leave it. Okay, how much is remaining though? Oh, quite a lot. So I will do only the comprehensions first, then we'll go to anything else. Operation number 3 actually. Okay, the solubility product of soluble salt is given by KSP is this thing. As soon as the product of the concentration of AY plus and X must become more than this KSP salt becomes precipitate, it may be practically we notice that AgCl is very soluble salt. Okay, okay, okay. Solubility decreases dramatically in this and that. It may therefore be considered in presence of a common ion. The solubility of salt decreases. Okay, fine. KSP of SRF2 in water is this thing. The solubility of SRF2 in 0.1 molar NaF. NaF strong electrolytes completely goes away, right? So almost 0.1 is the concentration of F minus, I think, right? It doesn't change much. So yeah, like that square, that's 10 power negative 2. So 8 into 10 power negative 8 would be the concentration of SR2 plus, which is very small in comparison to 0.1. So yeah, it kind of works. So there we go. The solubility is just 8 into 10 power negative 8, which is D. Hey, I didn't have to write anything. Cool. 11. Equal volume of the following two solutions are mixed. The one in which CaSO4 is precipitated. Oh, okay. So KSP is given. CaSO4, huh? So Ca plus N, Ca2 plus NiSO4 2 minus. We need that. Right. Wait, what? CaCl2. CaSO4 should precipitate. Oh, wait. Okay. CaSO4. But sulfates don't precipitate, do they? Okay, sulfates are like very soluble. So why would that reaction be like? I don't know. And CaCl2 doesn't precipitate. Okay, yeah, Ca is actually kind of ionic, so it works. If it was ECl2, that would be a different case. Anyway, equal volume of the following two solutions are mixed. So we will assume that CaCl2 doesn't precipitate. Okay, then it just completely dissociates, and then so it's 0.02 Ca2 plus and oh god 0.004 SO4 2 minus, right? So 2 into 10 power negative 2, 4 into 10 power negative 4. So 10 power negative 6 and 8. Okay, 8 into 10 power negative 6. That's 0.8 into 10 power negative 5. That's less than KSP. So no, A doesn't work. C, in C, instead of having 0.8, it's 1.6, but it still doesn't work. Okay. In B, it is, oh, it's even less. No, no thanks. B, it's 0.3 and 0.04. Hey, look, that's a whole factor of 10 over here. So it will work, right? It's going to be 3 into 10 power negative 2 and 4 into 10 power negative 3. So it's 12 into 10 power negative 6. It will work. So 11th D. The pH of a saturated solution of this guy is saturated solution, huh? Ah, that just means one in equilibrium. Right, so the pH of that. So its KSP is, oh yeah, MgOH by 2 it precipitates. I know. So 4 into 10 power negative 2. Right, so it's just like S cubed because, no, S into 2S squared. So 4S cubed is, oh, we cannot directly do it. So 4S cubed is 4 into 10 power negative 12. S will be 10 power negative 4. And yeah, that's much bigger than 10 power negative 7. So it works. So it's going to be 2 into 10 power negative 7. That's our OH minus concentration, which means our pH is 14 minus log base 10 of, what was this, 2 into 10 power negative 4, which is 14 plus 4 minus log base 2 of 2, which is minus 0.3. So this is like what's this, like 3.6, no, 3.7, so 17.7. That's pH, but that's too big. Something's wrong about it. Oh yeah, it's minus the POH, and POH also has that minus, so it should be plus of that. So then it will be negative positive, and now it will be 10.03. So 10.03 is C, 12th C. All right, next question. Next is comprehension for 4. For a weak acid solution, there's even more comprehension. So there's 2 of them that are remaining. Fine. For a weak acid solution, HA gives H plus plus A minus. As H plus increases, A minus decreases. Okay. And this thing increases. Okay, whatever. But HA need not be ionized. Okay, fine. In the diagram is shown fraction of protonated and deprotonated forms of 2 weak acids, HX and HY. Really? Wow. Right. So, and what's this thing? Fraction. This is pH. So as the pH changes, your fraction of what? Fraction of what? Come on. Oh, okay. A, B, C, D. What? What the heck? What does this even mean? What fraction of what is this? Come on, man. Label your diagrams correctly. Anything is given? No. Nothing's given about what this fraction represents. We'll assume that it represents the fraction of HA, because they said that you are adding H plus and that will change it. So we will assume initially it was only HA, or like a lot of HA basically. Okay, then it's gonna decrease as your wait, what? No, pH increases and this decreases. Yeah, that's correct, right? Because yeah, in acidic mediums more HA, in basic mediums less HA. Fine. After carefully analyzing different intersection points, their abscissa ordinate. Okay, answer which of the line represents protonated form of the stronger acid? Stronger acid. Oh, well, both of them go down the same intercepts. And okay, so this guy, for some particular pH, B is having more fraction of H plus, sorry, of HA, right? Or HB if you want. Okay, stronger acid. That just means one with a bigger K value. So K value is just concentration of H plus, which is the same for both, times concentration of the protonated form. Sorry, the deprotonated form, right? Upon the protonated form. And since this is basically the fraction of the protonated form, we want that to be the least so that you can get the maximum K value. Right. I mean, if that's less, then automatically fraction of the deprotonated form will increase. So that means A is in fact a stronger acid, because you need even more pH to actually push it back to its deprotonated form. Sorry, to its protonated form. So it wants to say its deprotonated form is a stronger acid. So yeah, A works. And right, so 13th A. Okay, 14th. 2 lines which can represent fraction of protonated and deprotonated forms of the same acid. What? Okay, 2 lines which can represent the fractions of protonated and deprotonated forms of the same acid. Oh, I understand. Anything about Ka values are given? Okay, nothing. Okay, let's look at C and D. Okay, so if these represent the deprotonated forms, then Which of them matches with which of them? That's what we are seeing. So let's look at this. Your x plus 1 minus x must be constant, right? So over here, its x value is smaller, so its 1 minus x value must be bigger. That means A and C, those match up, and B and D will match up, right? Yeah, A and C is matching up at 0.5. So A and D match up at this point, which doesn't make sense if it's just like if these are conjugate acid base pairs. So no, A and C and B and D. A and C and B and D. That's C and D over there. Options C and D. Okay, cool. Yeah. Ratio of Ka stronger acid upon Ka weaker acid. Oh god. Oh hey, that's nice. Like when fraction is 0.5, your pH, that's the same thing as your pKa, right? So over here for A, that's a stronger acid. Your pH value is, sorry, your pKa value is, okay, so like here, that's 5 maybe. So it's 10 power negative 5, that's Ka for stronger acid. And for weaker acids, it's 10 power negative 7. So yeah, it's 100. 15th B. One could have also gone with this, but it's not pKa, so B. Wow, seriously, they also put these kind of options over here. Cannot be solved. Okay, question number, sorry, comprehension 5. At high temperature, KSP of AgCl is 10 power negative 5, KSP of AgBr is 10 power negative 7 in a 1 liter solution. Its concentration of Cl minus is given, Br minus is given, Ag plus in terms of Ag is externally added. Initially, entire Ag plus added remains in the solution. Slowly, as the solution starts getting saturated, okay, precipitation starts. So a fraction of R added remains in the solution, and rest is PVDing out. Yeah. Also 16, 17 are the only questions. Wait. Oh, so you gave the KSPs. Hey, that's nice. This guy's KSP is bigger than this guy's. So that means, and the Cl minus and Br2 minus concentration are the same. So first, AgBr will start to precipitate out because it just needs 10 power negative 5. This needs 10 power negative 3. Right, so 10 power, we will have to wait till 10 power negative 5 for Ag plus. What's this? Ag plus solution. What about it? Oh, concentration of Ag plus in solution versus Br minus in solution. Right. So it's a line, of course. No, it doesn't look very good. Over here, so when is it 0? When it's 0, it's at equilibrium, of course, and that means, well, that's kind of weird actually. Yeah, it just hits a constant, right? After your, yeah, like your Ag plus concentration just starts being constant when, no, wait, the more Br minus you precipitate, the more Ag plus can be there in the solution, right? So it starts at 10 power 5, negative 5, and when does it end? Like when does the concentration of this guy, okay, what's this line doing? So Ag plus is 0 when Br minus is 10 power negative 2, yeah, okay, and then it linearly goes like this. Okay, no, it doesn't go linearly, because it's like xy equal to constant. It's that kind of curve. So this is best represented, right? So first it was 10 power negative 2, okay, right? Then as you add more Ag plus in there, so okay, I see what's happening. So across this whole thing, across, like I'm marking with my pointer, so in this rectangle, like as you are going up, your Ag plus concentration is increasing, nothing's happening to Br minus, and then it starts to decrease suddenly with this hyperbolic kind of trajectory for this graph, which is correct. So 16C, right? It's xy equal to constant, that kind of thing. It's a rectangular. We'll find the precipitation of AgBr before AgCl. Hey, I should have read this before that, then it would have been solved directly. When AgCl just starts precipitating, what am I saying? The total moles of AgNO3 externally added till this point is, total moles of AgNO3 externally added till this point. What's the big deal about it? It's like 10 power negative 5, yeah? Like, that's the Ag plus concentration. And wait, when AgCl just starts precipitating, fine, till this point. So yeah, okay, from forever, fine. So first, when does actually this happen? Like, so both of them must be at equilibrium, right? Right. So think about it. Ag plus Br minus Cl minus, these are at 10 power negative 2, 10 power negative 2, and Ag plus, we will be starting at 10 power negative 5. That's when this starts precipitating. And then this will be 10 power negative 5. Well, we just keep on adding it anyway, right? And it keeps on being in equilibrium. Yeah. And when this starts precipitating, AgCl starts precipitating, your Ag plus concentration must be 10 power negative 3. Right, so it went from that to that. Wow. And what's your Br minus concentration? Your Br minus concentration must be 10 power negative 4, right? Because it must be the same, right? And your Cl was just like this guy, right? So no, it's 10 power negative 2 over there, and that's 10 power negative 5. Yes, it makes sense. It makes perfect sense. Yeah, so we got the concentration. I just need to find how much of Ag plus was actually added. So Br minus went from 10 power negative 2 to 10 power negative 4. So where did most of the Br minus go? It just went to, hey, wait, you want without approximation. Oh, okay. Then it's 0.02 minus 0.01 minus 0.0001, right? It's 4 of these. That's how much Br2 was initially. Now only this much is left in solution. Rest of the Br2 that went with Ag plus, so that will give us the amount of Ag plus that are precipitated. Okay, that's good. And plus the amount of Ag plus that is still in the solution, that's 10 power negative 3. So that's going to be 10 point, yeah, it's still in the solution, right? Cool. That's how it should be. Yes, pretty sure of it. So 0.001. So you could just write it like that. Then this will be 0.0109. And where is it? D? D is the thing. So that's it. Comprehension type done. Next, matrix match type. We'll do it later. Then this thing, I don't know if I'm going to do it or not. Then some actual questions. Right, so I'll see you guys in the next video. Bye.